Okay, so a very good afternoon, everyone. I welcome you all for the Strength of Materials lecture series with the code 18CV32. So, in the morning session, we had started with Mohr circle, right? A graphical method to find out all the stresses, right, in a two-dimensional stress system. And we had seen the construction of Mohr circle, how to construct a circle, what are the different points to be considered in a Mohr circle, and what they actually represent, right? Maximum principal stress, major principal stress, minor principal stress, shear stress, and the planes, right? 2 theta and 2 theta 2 and so on. So these are the things which we have discussed in the previous session. And today, that is in this class, we shall continue on the Mohr circle numerical examples, right? So construction part we have already studied now. So now we'll look into the numerical examples of the uh, Mohr circle, right? So let me continue the numerical examples now. Is the slide visible to you all? Yes.
Yes, ma'am.
Okay. So let me continue this again. So I welcome you all for this Strength of Materials lecture series. So as I said in previous session, we had discussed of Mohr circle and its construction, right? And we had discussed all the points in the Mohr circle, what it indicates regarding the stresses, major principal stress, minor principal stress, maximum shearing stress, and where exactly you can measure the plane of maximum principal stress as well, right? So in this class, we'll continue the Mohr circle itself, but we shall see the numerical examples on the Mohr circle, right? So let me continue with the numerical examples. So is the slide visible to you all?
Yes, ma'am.
Okay, fine. So please read the question as it is shown to you, right? See, you're given the problem, you can solve it either by graphical method or by the analytic method, because in both the ways now you are well acquainted, right? So you have different formulas to calculate the maximum principal stress and minimum principal stress and so on and so forth, as well as you have also studied the Mohr circle now. So in both the ways you can calculate the given conditions, okay, given questions, right? So as far as VTU exam is considered, however the question is asked, you should answer, right? So if they ask you through analytic method, you can go for that. If they ask you through Mohr circle construction, you can go for that. So as the question states here, a point in a strained material is subjected to stresses as shown, right? So a figure has been shown to you, a two-dimensional stress system is clearly visible to you, right? And you can see this tensile stresses, right? Direct tensile stress on all the faces. Sigma x, you have 65 Newton per mm square, and you have sigma y, that is 35 Newton per mm square, and at the same time you have this shearing stress, right? So you have this shearing stress that is 25 Newton per mm square, right? Now your question is using Mohr circle method. Okay, your question is using Mohr circle method, determine normal and tangential stresses across the oblique plane. So you have an inclined plane, oblique plane in the sense inclined plane. So you have an inclined plane which is inclined at an angle of 45 degree. Okay, it is inclined at an angle of 45 degree from the minor axis. Okay, so the meaning of minor axis, I have told you already this minor axis and major axis. Let me say this once again. See, direct tensile stress, which is maximum? Sigma x is maximum or sigma y is maximum? Now, irrespective of positive, negative, you should answer me. Of course, here both are tensile, but irrespective of compressive and tensile, just see sigma x and sigma y, that is direct tensile, direct stress. In both the direct stress, sigma x and sigma y, which is higher and which is lower? Yes? Can you answer me? Yes? Am I audible? Yes? Can I get the answer?
Yes, ma'am.
See, you need to answer to my question every time. See, because what happens is when I ask you a question, when I see the silence, then I need to think twice whether I'm audible to you or whether I have come out of the class. Now, since this is online class, you need to interact with me. Then itself, I can get to know what is your state of understanding, right? Whereas in the class, we would have understood just by your looking at your faces. Now it's like, I need to understand whether you people are hearing my question or whether I'm audible to you, whether the slide is visible to you, right? So every time, at least you can answer me no, at least, so that I'll get to know that I'm audible to you. Okay. So now, so there are two tensile stress, as you can see here, sigma x, sigma y. Sigma x is 65 Newton per mm square. Sigma y is 35 Newton per mm square. So which is greater now?
Sigma X, ma'am.
Sigma x is greater, right? And sigma x, as you can see here, you can see the direction how it is acting, sigma x. So the axis on which the sigma x is acting, so the x axis, so it is acting along the x axis, right? So this axis, the axis is nothing but an imaginary line. Okay, so that imaginary line which is passing through the center of your body, right? In the x axis, in the direction of x, right? Because you're talking about major, that is 65. So this is called as a major axis. Now along the 65, the major axis is passing, right? Now along the 65, the major axis is passing, and 35 Newton per mm square. As you can see here, 35 Newton per mm square minor minor axis, right? So why it is minor axis? This y-axis along the 35. This we call it as a minor axis because the direct tensile stress is less over here. So I may call this the axis or the imaginary line along which this 35 is acting. This is minor axis. So you can show the dotted lines also. The way how you used to show it in while calculating moment of inertia in your first year. Okay, you used to determine the CG and you used to draw the dotted lines at the center. Do you remember that? Yes?
Yes, ma'am.
Right. In the same way, you can show it here. Where is your major axis? Where is your minor axis? Now, always, now why I said this, because why I went on explaining this concept, because see, you have an inclined plane here, right? You have an oblique plane or an inclined plane, which is inclined at 45 degree. From where it is inclined at 45 degree? So usually in the question, they'll usually mention it, or you need to understand it. It is inclined at an angle of 45 degree from, you tell me first whether it is inclined from major axis or minor axis. Anybody? It is inclined at an angle of 45 degree from major axis or minor axis.
Major axis, ma'am.
Think once again. Major axis or minor axis? See, major axis, it is passing along x-axis. Minor axis, it is passing along y-axis. Is it not?
Minor axis.
Minor axis, ma'am.
Right. 45 degree, it is an angle subtended from minor axis. Now, did you get my point? Or you want me to understand? Explain
Yes,
this
ma'am.
once again. Right. See, major axis, it is passing along x because 65 is higher. Minor axis, it is passing along y. Major and minor. So now your angle 45 degree, it is an angle, it is subtended by an angle of 45 degree from which axis? From minor axis. From y it is subtended, right? So instead of calling y axis, I'll call it as a minor axis. So that's how it is usually given in the VTU question papers, right? So don't confuse with that. So this is how the understanding goes, right? So is the question understood to you all?
Yes, ma'am.
Okay, fine.
Yes,
Okay.
ma'am.
So, right. So, in this particular question, the things which you have given, the things which they have given to you is one is sigma x, one is sigma y, and they have given you angle theta 45 degree, and they have given you q, that is 25 Newton per mm square. Okay. Now, let's see from graphical method how we'll be able to solve this problem. See. Now, first of all, instead of going to graphical method directly, let me solve this problem by our analytic method, that is by using the formulas. So these answer I'll compare with the graphical analysis, okay, so that you will understand it in a better way. Okay, so now, so they have asked you to find out the normal stress and the tangential stress. You know the formula for the normal stress. So it's sigma n, I have written it here, right? So I have written the sigma n formula here. So sigma n formula, of course, sigma n formula, according to you, I had taken the notation of sigma x and sigma y. Okay. So instead of writing sigma x, sigma y, they have written sigma 1 and sigma 2. Please make a correction. And you, of course, it's not a correction. It's the way how you understand it. So instead of using sigma 1, sigma 2, you can use sigma x, sigma y. Because according to our concept, we have used sigma 1 and sigma 2 for major principal stress and minor principal stress, right? But actually in this formula you have sigma x and sigma y. You can use the same thing. Okay, so sigma n is equal to sigma x plus sigma 2 divided by sigma x plus sigma y divided by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau sine or q sine 2 theta. This is your actual formula. So substitute the values. Already it is given in the question. Substitute, operate in your calculators with patience, and you will get an answer as 75 Newton per mm square. Right? Now, similar way, tangential stress, that is sigma t. Now, once again, don't use sigma 1, sigma 2, use sigma x, sigma y. Sigma t is equal to sigma x minus sigma y by 2 sine 2 theta minus q cos 2 theta. So, in this, once again, you substitute, you will get an answer 15 Newton per mm square. So, normal stress, according to analytic method, you have got 75 Newton per mm square, and tangential stress, you have got 15 Newton per mm square. So, this is an analytic method. So, now actual question is to find out by the graphical method. Okay. So, let me show you by using graph, how can you solve this problem. So, this is a Mohr circle method. The same problem, I'm showing it by Mohr circle method. Okay. So please understand the first line what I've given. The first line indicates the given condition. See, once again, given condition, instead of writing sigma x, it has been written as sigma 1. So I have already told you, different textbook will follow the different notations. But we had followed sigma x as direct stress, right? So instead of writing sigma 1, you can write sigma x. So sigma x is equal to 65 Newton per mm square. And remember that is tensile, right? How did you get to know whether it is tensile or compressive? Looking at the diagram. So it has already been given to you, right? So 65 is tensile. Similarly, sigma y, instead of writing sigma y, it is written sigma 2 here. So sigma y is 35 Newton per mm square, right? Now, I've already told you, whenever you'll be solving graphical method, you need to acquire some scale, right? So as you usually know, whenever you will be drawing any graph, right, a 2D, two-dimensional graph, you always, first thing is you always choose the scale, right? So a scale should be chosen very carefully, depending on the values, whether it will fit in your graph or no. So the scale I have chosen here is 1 centimeter is equal to 10 Newton per mm square, right? 1 centimeter is equal to 10 Newton per mm square. And the Q is given to you, that is 25 Newton per mm square, and theta is given to you as 45 degrees. So this is my given condition. Now let's see how to solve this, how to plot a graph. Now after this class, I want everyone to get a graph. Okay, I hope nearby your house or anywhere you can get a graph sheet, right? Take that graph sheet and plot it yourself. Okay, that makes you to get the interest, and that makes you to be perfect in this concept. So just by observing this class or just by observing the notes, you will not understand this unless and until you draw with your own hands the circle and you calculate all the values. So I want everyone to take a graph sheet and plot this graph. So what you will do here is, at the left side, at the right side, I have shown you the points. So the first point says that take any point A. Now in the while construction, I had taken this point as O. Here they have taken it as A. Okay, so you can, of course, you can always change the notations, alphabets, however you want. Okay, so take a point A and draw a horizontal line through A. So I have just made a graph sheet, x-axis, y-axis. So I have marked the point A. From the point A, I have drawn the horizontal line. Okay, so this horizontal line indicates the direct stress axis. And from the point A, I have drawn the y-axis. This indicates the shear stress axis, that is y-axis, right? So x-axis, y-axis. Next, second point. Take AB. Okay, take AB length. So AB, what should be your AB? See, if you remember my today's first hour class, right? So after taking the point A or the point O, first thing we had done, we had marked the point F and G, right? So same way, take F point and G point. So what is the coordinate for the F point? Sigma x comma q, right? If you remember that, the coordinate of F is sigma x comma q. So sigma x, in the sense, it should start from A to B. So that is why it is given as A to B sigma x. So it is taken as 6.5 centimeter. How it is 6.5? Anybody? How it is 6.5? How did I take 6.5 centimeter? Because your sigma x is 65 Newton per mm square, and our scale is 1 centimeter is equal to 10 Newton per mm square. So 65 divided by 10, you will get it as 6.5 centimeter. So A to B, take it as 6.5 centimeter. Similarly, A to C, that is about G coordinate. So G coordinate is sigma y comma q, right? So A to C, it is 3.5 centimeter, because the answer is 35 Newton per mm square. So plot this. After this, drop a perpendicular, right? So it has been shown here, draw perpendicular at B and C. Draw perpendicular at B and C. Okay, how do you, up till what extent you will draw the perpendicular? Because we know that the length of GC or BF is shear stress, that is Q, that is 25 Newton per mm square. In the sense, when you convert it to scale, it becomes 2.5 centimeter. So if you observe here carefully, 2.5 centimeter is also very clearly shown to you. So this 2.5 centimeter at both the sides we have drawn. After that, with the help of protractor, so take the radius equal to GO or OF and draw a circle. So now the circle has been drawn, right? Now after drawing a circle, take a protractor. Okay, so keep your protractor on the line OF. Okay, so keep your protractor on the line OF. After keeping a protractor on the line OF, we know that theta is 45 degree. So the 2 theta value becomes 90 degree. So 2 theta, using protractor, mark the point 90 degree on a circle. It will come to a point E, right? So E is the point. So this point E, just mark it and join OE, and also drop a perpendicular ED and also join AE, right? So you need to join all these points now. Now once all the points have been joined, now just your next step is simply go on measuring all the distance. So the distances are, now actually in this particular problem you are calculating sigma n and sigma t. So I have already told you the coordinates of E are sigma n comma sigma t. So as such, it indicates, that is, if you measure the point A to D, if you measure the point A to D, it indicates sigma n, that is normal stress. at the bottom it has been shown to you sigma n is equal to length of AD into scale. Again, you need to apply the scale as well. So length of AD, you will get it as 7.5 centimeter multiplied by 10, you will get it as 75 Newton per mm square. Now that means this is actually matching with my analytic method. So graphical method as well as analytic method, they are giving you the same results. Right? Now, also tangential stress. How do you get the tangential stress? If you measure the length ED. So the length ED is length ED into scale, that is 1.5 centimeter you have got. 1.5 into 10, you will get it as 15 Newton per mm square. Now, once again, these two values are coinciding with my previous slide, that is analytic method values. So this is all about the Moore circle. So all these results have been matching with my previous results. Of course, in this particular problem, they have asked you only normal stress and tangential stress. If they would have asked you about uh, major principal stress and minor principal stress, even that you can measure. So can you tell me major principal stress sigma 1 from where to where I should measure in this particular graph? Anybody? If you have carefully listened to my first hour class today's first session, then you should answer me from where to where I should measure to get the answer for major principal stress sigma 1.
From A to D.
Sorry,
A to D.
A to
D.
D. See, A to D is sigma n, normal stress. I'm talking about major principal stress sigma 1. In the previous session, I had shown the dotted lines with the help of red color. Major principal stress, minor principal stress. Remember? So in this, of course, in this problem, they have not asked you, but if the question is given to you, also locate major principal stress and minor principal stress. So where to where you will measure it? This has been explained in today's class. Yes, anybody? You don't remember? Yes? Okay, fine. So you need to measure. So if you remember my today's class, I had marked the point with the help of a red ink. If you measure the distance from A to M, okay, so M is the end point of that circle. So A to M indicates the major principal stress. And what about minor principal stress? A to
L.
L. L, very correct. A to L indicates the minor principal stress, sigma 1 and sigma 2, major, minor, right? And of course, in this particular problem, instead of taking sigma x, sigma y, he has taken sigma 1, sigma 2. You can interchange it. Okay. So actually, in our concept, we have taken major principal stress and minor principal stress as sigma 1 and sigma 2. Direct stress, we had taken sigma x and sigma y. Okay. Here it has been interchanged. You can change it anyhow. Okay. And so if you want to get maximum principal stress, then you need to measure the S. Of course, S is missing here, but S indicates a straight line which joins from O to top, right? So that is yes, maximum principal stress. And another point is, what about the directions? Principal plane direction 2 theta. Of course, it has already been given. Still, you can measure with the help of protractor, right? So this is all about the first numerical example. Let me shift to the next numerical example now. So observe this carefully once again. So at a certain point in a strained material, the intensities of stresses on two planes at right angles to each other are 20 and 10 Newton per mm square. Both are tensile, right? So instead of giving you through diagrammatic representation, instead of giving you a 2D block and showing where is sigma x, where is sigma y, so he has given it you in the form of sentence. So at a certain point in a strained material, the intensities of stresses which are at the two planes which are at right angles. We know that sigma x and sigma y always at right angles, perpendicular. So he has given you right angles at each other are 20 and 10 Newton per mm square. Okay, and both are tensile. and they are accompanied by shear stress, which is at a magnitude of 10 Newton per mm square. So sigma x is given, sigma y is given, and q is given to you. So here it has been taken as once again sigma 1, sigma 2. You take it as sigma x, sigma y, and q. Okay. Now your question is find graphically or otherwise locate the principal plane and evaluate the principal stresses. So you should find out theta 1, theta 2, and you should find out the principal stresses sigma 1, sigma 2. This is your question. So first write the given conditions, that is sigma x is equal to 20, sigma y is equal to 10, q is equal to 10 Newton per mm square. So now always choose a scale, right? So I'll choose a scale 1 centimeter is equal to 2 Newton per mm square. So 1 centimeter is equal to 2 Newton per mm square, in the sense sigma x, or in this case sigma 1, sigma x becomes 20 by 2, that is 10 centimeter, and sigma y becomes 10 by 2, that is 5 Newton, 5 centimeters, and q becomes 10 by 2, that is 5 centimeters, right? So is the given condition understood to you all? Yes? Is the given condition understood to you all?
Yes, ma'am.
Okay, now the same thing I have written at the top here once again. Sigma x is 20, sigma y is 10, q is 5 centimeters, and scale is 1 centimeter is equal to 2 Newton per mm square. Okay, now just see at the right side I have given the procedure. Now once again take a point A, draw a horizontal line and vertical line which indicates x-axis and y-axis, that is direct stress and the tensile shear stress. Okay, now after this take sigma x. What is sigma x? 10 centimeter. So from A to B take 10 is it 10 or 20? Oh sorry, 20 centimeters. Let me cross verify this. Okay, sigma x is 10 centimeters, sigma y is 5 centimeters. Okay, so okay, from A to B, take 10 centimeters distance and mark the point B. Similarly, from A to C, mark the point C as 5 centimeter. After this, raise the perpendicular CG and BF, that is 5 centimeter because Q is 5 centimeter. Now with the help of protractor, take OF or OG radius, draw a circle. So now your circle is ready now. Okay. Now once this circle is ready, of course, theta is not given to you in this question on which plane you are supposed to determine. He is just asking you what is the magnitude of major principal stress, minor principal stress, and the direction of major principal stress. That is the only thing he has asked you. So to find out the direction, what you should do here is take a protractor, keep it on the line OF. Okay, after keeping it on a line OF, measure the angle, that is FOB. Measure this angle. We had taken it 2 theta. If you remember, while I was showing the proof of Morse circle, derivation of Morse circle, right? There I had taken 2 theta. Remember that, right? Yes or no? So 2 theta angle, which indicates the direction of principal plane, right? So the same thing you need to measure here. So measure this angle FOB by using a protractor. So this angle 2 theta, so you will get it at as 63.7. You can see here at the top it has been written below the Morse circle. The angle you will get after measuring the angle, you will get it as 63.7 degrees. So when 2 theta is 63.7, so instead of calling 2 theta, you can call it as 2 theta 1 also, not an issue, because there are two principal plane, right? So 2 theta is 63.7, and what about theta? It is 31.85. When 2 theta is 63.7 divided by 2, you will get it as 31.85. So this is the value for theta 1. Now, if you want to get the value for theta 2, you can add plus 90 degree. Okay. Now, another very important point you should note down here is, see, observe these two lines carefully. Okay. Observe the two lines carefully. That is your OM and OL. Okay, is it not they are differing by 180 degrees? Yes, they are differing by actually 180 degrees. So it clearly indicates that 2 theta 1 and 2 theta 2 both actually differ by 180 degrees, or theta 1 theta 2 differ by 90 degrees. So even that you can clearly observe in this particular graph. Okay, so 2 theta 1, 2 theta 2 both can be measured here, or else even if you measure only 1 theta and just add it by 90, you will get the second theta 2 also. Okay, so this is about the principal plane. Now to measure the principal stresses, major principal stress and minor principal stress, what you will do here is measure A to M distance. So A to M indicates major principal stress, A to L indicates minor principal stress. So that is also shown to you. Length AM into scale, at the top it is written 13.1 centimeter you have got. So 13.1 into 2, you will get 26.2 Newton per mm square. This is your sigma 1. Similarly, sigma 2, bottom it is written minor principal stress. Length AL into scale, that is you have got 1.91 centimeters, multiplied by 2, you will get it as 9.82 Newton per mm square. Right? So you can, of course, by using these values, you can solve by analytic method, you can cross verify. Okay, so is this problem understood to you all?
Yes, ma'am.
Okay. So let's see a last example from numeric Morse circle. So element cube is subjected to tensile stress 30 Newton per mm square and 10 Newton per mm square acting at two mutually perpendicular planes, and shear stress 10 Newton per mm square on these planes is given. Right? Draw the Morse circle and hence otherwise determine magnitude and direction of principal stresses and also the greatest shear stress. So now another important point has been asked to you in this particular question is you should find out magnitude of maximum shearing stress. That is, he is asking you to find the distance of OS. Okay, so it's the same problem, only thing is an extra maximum shearing stress has been asked to you. So I have written here once again sigma x 30 Newton per mm square, sigma y 10 Newton per mm square, tau is 10 Newton per mm square, and take a scale 1 centimeter is equal to 2 Newton per mm square. You say suppose sometimes 1 centimeter is equal to 2 Newton per mm square depending on the values. If you are getting a very small graph, you can always take 1 centimeter is equal to 1 Newton per mm square. So however you want, you can choose your scale. Okay, so just convert the scales. So sigma x becomes 30 by 2, 11 is 15 centimeters. Sigma y becomes 10 by 2, that is 5 centimeters. Okay, now plot the graph by using all these values. Now follow the same procedures. Okay, the procedure remains same. I have already explained it before. Okay, so by taking a distance A to M, that is 15 centimeter, and A to C 5 centimeters, mark it, draw the circle. Okay, after drawing the circle, measure this 2 theta value. So 2 theta you have got it as 45 degree, so theta becomes 22.25. Okay, and measure the length A to M and measure the length A to L. So major principal stress and minor principal stress. So you have got the answers. It has been already shown to you. Major principal stress is 34.2 Newton per mm square. Minor principal stress, you have got it as 5.86 Newton per mm square. So you can plot this. And very important point, another point has been asked to you in this question is maximum shearing stress. So OS, if you remember while in derivation, I have shown to you how to calculate maximum shearing stress in the graph. You need to measure the OS. So here in this case, it has been taken as H. So a line has been also shown to you maximum shearing stress line. So measure the distance O to H. This indicates the maximum shearing stress, right? So maximum shearing stress OH has been shown to you. Measure this and convert this to the scale. You will get an answer for maximum shearing stress. Okay, so that's all for this Morse circle and numerical examples. I hope these problems have been understood to you all. See, another point I need to tell you is, suppose instead of see sigma x, sigma y in all the three cases, it was tensile, so you have drawn it very easily. Now suppose if sigma x is tensile and sigma y is compressive, then what will you do? Because in a two-dimensional system, you may get a tensile or you may get a compressive. Then how do you proceed? See, what you should do here in that case is, I have already told you, uh, tensile stress, take it as positive. Compressive stress, take it as negative in the sense, okay, suppose your origin is here, right? You have your origin at A point now. O is the center point, A is the origin point. Okay, from the origin, right side of the origin, all are positive values. Left side of the origin, all are negative values. We know this fact. Okay, in a Cartesian coordinate system. Suppose if they give you any 10 direct stress as compressive stress, then you need to alter the values depending on the origin. You need to take it at the positive or negative side in the Cartesian system. That's how you need to follow. Okay, is this understood to you all? Yes.
Yes, ma'am.
Okay.
Yes,
So
ma'am.
be very careful while plotting the graph. If you get any compressive stress, if you get any direct stress negative, that is direct stress, if you are getting it as compression, if the given condition is direct compressive stress, then it comes in negative side because it is negative according to our assumed direction. I have shown you the sign conventions in the previous session. Okay, so compression, it is taken as negative. So accordingly. So even while drawing the 2D graph, you know how to take positive, how to take negative in the graph. In the same way, you should take it here as okay. So be very careful while taking positive, negative signs and draw it accordingly. Okay. So I hope these graphical method, more circle is understood to you all, right? And the numerical example is also understood to you all. In the next session, we'll continue with the third module, that is uh, shear bending moment and the shear force diagram, SFD and BMD diagram. Is there any doubt in this particular chapter on this particular concept? Now, as far as VTU exam is considered, you may get a question like, describe Morse circle and please write down the construction of Morse circle. You may get it for 8 to 10 marks, right? So usually the question is define Morse circle and write the construction of Morse circle. In the sense, you should define it, you should draw the graph, I mean just a general graph of Morse circle, and you should write the construction, right? So construction I have explained in the morning session, the same thing you can explain the construction. And if it is for more marks or if they ask you the proof, then you need to write around 3 to 4 equations about the proof, right? So why all these stresses will be taken in circle? How do you get to know that this is a circle? This circle will give you the compound stress, all the stresses. So whatever we have proven in the morning session, that is the equation of a circle. Okay, with the help of sigma n and sigma t, we have got that equation of a circle. So that you need to prove, right? Or otherwise you may get a numerical examples on this Moore circle. So of course in video booklet at the initial pages you have the graph sheet also. Here you can draw the graph sheet. Okay. Usually in as far as second module is considered compound stress, usually you will get analytic method numerical examples. Very rarely you may get Moore circle numerical example. But construction of Moore circle, it is usually you will get a question. Define Moore circle and construction of Moore circle. Okay. Do you have any other doubt to be discussed?
No, ma'am.
Okay. So that's all for this today's session. So to summarize, today we have learned construction of Moore circle and we have solved numerical examples, that is graphical method numerical examples on the Moore circle. Okay. So that's all for this today's class. Thank you.
Thank you, ma'am.